I am happy to introduce our first set of speakers, two friends of mine, Doctors Lee Allison and Brian Conway. Lee holds a Ph.D. in nuclear physics from Old Dominion University, specializing in particle detection. He is now an RSM research staff member at IDA, where he focuses on cyber operational test and evaluation of naval platforms along with land warfare. Lee has also helped to develop and build one of IDA's cyber lab environments, which we use to train our sponsors and others in the community on basic cyber T&E concepts. Brian holds a BS from Notre Dame and a PhD from Penn State in chemistry. He joined IDA in 2019 and has since supported OT testing in both DoD and DHS. Here he focuses on naval and net-centric cyber, looking at how mission effects impact the warfighter. And with that, I will pass it off to my colleagues. Thank you.
All right, thanks for the introduction, Mark. I'm Brian Conway. I've been at IDA now for about 4 years. Mark told you about everything I'm working on. So today we're going to be talking about planning for public sector commercial cloud testing. Director Gerton, during his introduction today, was talking about testing the way we fight. One of those things is going to be testing in the cloud. This is something that we're already doing. I'm going to get into a little bit on how the United States government is moving into the cloud in a couple slides. But with that, let's get rolling. So I'm going to start off with an example of a potential cloud exploit that actually happened in the news 2 months ago. So here we have a regional airline, Commute Air. They are a subsidiary of United Airlines. They operate some flights in the Midwest. And they're responsible for maintaining their own computer networks. And one of the things they do is they operate pretty heavily in Amazon Web Services, AWS. You'll hear me say that a lot today. And they've got their own continuous integration, continuous delivery, DevSecOps pipeline for deploying software. And one of the ways they do that is through this server called Jenkins, which stages and tests and deploys your software. Unfortunately, a hacker came across this Jenkins server, which was floating around on the open internet, and found that it was misconfigured and could pop it open and remote control the whole thing. And one of the things that they found inside this Jenkins server was a whole bunch of the code that was going to be deployed to Commute Air's operational environment. So the hacker goes through. This is I'm going to call this person a gray hat hacker. This is somebody who's just looking for systems to break and see who they're going to tell about it. In this case, they reached out to the media through a reporter at the Daily Dot. I've got the link here. So the hacker finds some source code that compares the TSA no-fly list to employees at Commute Air. So this hacker goes, well, that's interesting. Let me see if I can find that no-fly list. And sure enough, in the source code, there was the TSA no-fly list sitting in plain text. So the hacker was able to pull out that TSA no-fly list. But that's not all. Within the source code, they were able to recover some AWS credentials, which allows them to get access to Commute Air's AWS environment. And there, they were able to pull out a whole bunch of database tables that included their employee data, where they lived, social security numbers, all sorts of terrible, terrible things. So this is the sort of thing that we want to be able to catch when we're doing cybersecurity testing of what the government is putting into the cloud. And so the government should find these vulnerabilities and patch them before some hacker comes along and finds them for themselves. So today Lee and I are going to talk to you a little bit about how deployments look different in a commercial cloud versus a traditional on-premises environment. Talk about how connecting to a cloud system is a little bit different than connecting to an on-prem system. Wrap this up with another case study where we look at another hack that was in the news that took advantage of some of these vulnerabilities that the customer is responsible for in the commercial cloud. So like I said, the public sector is rapidly shifting toward using the cloud. The top half of the screen, I have just a few organizations who are already operating pretty heavily in commercial cloud services. And on the bottom are a list of different kind of high-profile cloud service offerings that have been, and I'm going to talk about this in a second, FedRAMP approved for use in the federal government. This has been an ongoing shift across multiple administrations. I won't get into all the policy here, right? But this is both a DoD and really a federal government at large initiative. You'll probably recall the JEDI contract that was supposed to be the kind of the joint enterprise defense infrastructure, general use cloud across DoD that wound up getting canceled. That was at the time a $10 billion contract over 10 years. The DoD has recently shifted into a second contract, the Joint Warfighter Cloud Capability Contract, which is $10 billion over 5 years spread over 4 different providers. So don't get the sense that one cloud contract gets canceled, we're moving out of that space. No, the DoD is going there just as quick as ever. Likewise, the federal government has been pushing more steadily into cloud environments. And one of the ways that the federal government has tried to streamline cloud adoption across the DoD and the rest of the government is through the FedRAMP program. So the concept of FedRAMP is this idea that they will approve different cloud service offerings once so that they can be used many times across the federal government. So I'll talk a little bit about what that looks like quickly. So you can actually go to the FedRAMP marketplace. You just Google FedRAMP and you'll find it no problem. There's about 300 different cloud service offerings that have already been approved for use in the federal government through FedRAMP, and another 100 that are on their way to being approved. So on the right here, I'm just showing a sample from the marketplace. And like I said, I'm going to be talking about AWS a little bit today. AWS has over 600 different authorizations across the federal government. I won't read every single one of these off to you, but they encompass DoD, Department of Justice, CISA, the Cybersecurity and Infrastructure Security Agency. Really just about any government entity has its hand in AWS one way or another. But AWS is this big monolith, right? And so there's, as part of AWS GovCloud, there's actually a subset of all of AWS that's approved for government use. So this ranges from your standard compute instances like Elastic Compute Cloud, to database services, to AI and machine learning and IoT, Internet of Things. AWS is trying to be the one-stop shop for you to develop any software that you're going to deploy as an application. And not only is AWS itself part of government systems, but other FedRAMP approved cloud service offerings like CrowdStrike, Box, Salesforce, Zoom are all built on AWS themselves. So you inherit all of AWS's security when you're using those different services. Customers have some responsibility, though, when it comes to cloud service offerings. So you'll typically hear what's called the shared responsibility model, and that's what I'm showing here on the right side of the slide. So the cloud service offering, so I'll just stick with AWS as an example. When they provide something like infrastructure as a service, they're providing the hardware, the data centers, the networking, the infrastructure that you need, that you no longer need to manage. That's shown in blue on the right side of the slide. But depending on the cloud service offering that you decide to purchase, you might still be responsible for installing your own operating systems on some virtual hardware, or running the right version of Python or Java to run your application, actually deploying the code that runs your applications. And you're always going to be responsible for authenticating, managing the data, and configuring the systems that are part of the government's portion of a cloud service offering. You'll frequently hear these 3 service models: infrastructure as a service, platform as a service, and software as a service, IaaS, PaaS, and SaaS. These are trading off the amount of customizability in your cloud service offering for reducing your development time. So you're using a more complete product for something like software as a service, which would be like Zoom, where you're buying a pre-canned product and you're going to integrate that in your environment. Whereas you'll hear infrastructure as a service, that's more buying an AWS account and building out your own Elastic Compute services and so on. I'm going to get into that in a slide or two here. So testers should be taking advantage of these FedRAMP packages. So as part of FedRAMP, the federal government is doing some sort of evaluation to make sure that the cloud service offering is secure. So this involves bringing out a third-party assessment organization to take a look at what AWS is building into their cloud versus what the customer is actually putting there. So these are useful, and they certainly help inform our assessments, but we need to be doing our own assessments of what the government is putting into the cloud. FedRAMP does not provide any insight into what the customer is building itself in those service offerings. So just to give you a sense of the threats that are out there, the NSA put out a really nice white paper back in 2020. It's about like a 10-page read that summarizes some of the common cloud vulnerabilities that they've come across in the wild that have targeted DoD systems. So you'll see here on the plot, we've got supply chain vulnerabilities and shared tenancy vulnerabilities as these low prevalence, high sophistication vulnerabilities. These are the sort of thing that fall on the cloud service provider to remediate. It's AWS's job to make sure that customers can't pivot between each other's resources. But the low-hanging fruit here is this customer responsibility vulnerabilities, which is shown on the bottom right portion of this plot. High prevalence, low sophistication. Going back to the example I started the presentation with, this is getting the misconfigurations wrong on the Jenkins server and making sure that the Jenkins server is appropriately locked down so that someone can't break into it. Managing access control configuration are the things the customer needs to worry about. So now I'm going to shift gears a bit and talk about, well, what do these cloud service deployments actually look like compared to a standard on-premises data center? So here I'm showing a very simple web application where we might have a web application firewall that's accepting user traffic and allowing some through and rejecting others, passing it to a load balancing server that's going to distribute it across web servers to balance load for how many users are accessing your application at any point in time. Then you might have another load balancer that sits behind the web servers that's balancing to where your application is actually being hosted. And there might be some storage servers and database servers for pulling customer information or storing or loading static website assets. So the easiest way to shift this to the cloud is to just rebuild the whole thing in AWS or Microsoft Azure. So I was mentioning you have this idea of compute services, AWS they're called EC2s, Elastic Compute Cloud. In Azure they're called virtual machines. You're basically just buying compute space and you can recreate the entire network that you had formerly in a on-premises data center. So you would take your web application firewall and you'd buy some EC2 space and you'd load on a new web application firewall, you'd load an operating system and you'd build this out just like it exists in your current environment. Or you might have to manage your own database servers where you have to load on a particular version of MySQL and have enough database servers to respond to the load that you need to serve your website properly. One of the advantages of shifting to the cloud is this idea that you can rapidly provision and deprovision assets as needed. So now rather than having physical hardware where I need to buy a new web server and spin that up and get it ready to adjust to higher user demand, I can click a few buttons in AWS and create a new web server like that. But really, like I said, AWS doesn't want to just have you recreate your on-premises systems. They want you to be locked into their infrastructure. And so here I'm showing each of these major cloud service providers, Microsoft, AWS, Google, will provide services that you can use rather than having to maintain all of your infrastructure like it's in your on-premises data center. So on the right side of the plot now, I've swapped out a database server with Azure's Cosmos database service. So now no longer am I responsible for updating software and patching everything. All I do is I hand my data into the Cosmos database service and it seamlessly interacts with other AWS services and passes my data with the appropriate key management infrastructure to make sure that my data is getting securely from one place to another in the cloud. Azure's Cosmos database is just one example of a whole smattering of these services. And so AWS has their own web application firewall that you could use. I'm showing here, this is an illustration. You'd never use AWS talking to Azure like this, but I'm trying to get across the idea that each one of these cloud service providers has their own way of implementing a web application firewall or a load balancer, or AWS has the simple storage service, which is where you typically store any sort of static content. Google has its own SQL database. There's a lot of things that testers need to keep track of and understand how are these environments actually being deployed in operations, and how does this look different, and how do I connect to these services that's different about a standard on-prem deployment. So not only that, you can also configure all sorts of monitoring. So each of the major cloud service providers has their own monitoring services that you implement in your environment. Just showing here, AWS CloudWatch, Azure Monitor, Google Cloud Monitoring. These can all be configured for basically whatever type of monitoring you want to do. You can track API calls, you can track who is accessing particular services. You can use it for performance monitoring. Is my application drawing too much RAM, CPU power? Do I need to spin up more virtual machines or EC2s? So when it comes to cyber testing, it becomes interesting. How is the government customer buying monitoring services and implementing them in their environment? And how are they integrating those with their on-prem systems? So just to leave it off, I gave you a very simple example of how you could convert an on-prem data center to something that exists in the cloud. AWS provides a whole bunch of different reference architectures for how you can implement all their services to deliver some sort of application. Here, I'm not going to get into this whole thing, but this would be at an airport. If you have a bunch of cameras, you can track how are my lines growing as a function of time, and try to inform your staffing to respond to, oh, is the line getting long at baggage claim? Is there a problem down there? Or is the ticketing desk getting overloaded? So you can use your cameras, feed it all into AWS, use AI machine learning, and figure out whether or not you need to set up alerts and monitoring to respond. So these systems can get complicated very quickly. So with that, I'm going to transition this over to Lee, who's going to tell you more about how you can connect to the cloud. Yes.
Morning, everybody. My name is Lee Allison, and I'm going to be walking through the last half of this briefing today. So as you hopefully can appreciate after what Brian just walked through, these environments, these deployments can get very, very complicated very, very quickly. So testing, from a cyber testing perspective, we really need to understand what is deployed in the cloud and how we go about tackling those. But just as important as with any other cyber test is knowing what the attack surface looks like. For cloud offerings, the attack surface is really just how the various user roles go about interacting or interfacing with the cloud itself. So you can have something like a simple web login page to check your Gmail. If you're a higher privileged user, you might use a VPN connection to maybe deploy some software updates to a server. And then finally, you could use a command line interface if you were probably an administrative type user role. So going back to this toy model that Brian was showing earlier, if you're just a regular end user, like I said, you might interface with a web application login page, say like your Gmail login or something. You'll be routing traffic through this firewall application that will then send the traffic onto the rest of the services, and you'll have you'll get normal interaction with the cloud environment. One thing to consider, especially from the end user perspective, for an adversarial point of view, is what is publicly available knowledge, what are vulnerabilities and exposures of these commonly used web applications that I could take advantage of, or the adversary could take advantage of, to in some way weaponize or exfiltrate data from your cloud offering. So here we're just showing the top 10 open web application security projects, security concerns from 2021. Things like SQL injections and misconfigured access controls and things like that. So from a test perspective, again, it's very important to understand what is available publicly that could be leveraged that you really need to lock down in your cloud-based system. Moving on to more of a privileged role, like a developer, for example, instead of having to use that web login page to access the firewall to go through the services, they might have a direct connection via VPN tunnel, for example, to talk specifically to the web servers, the application servers, etc., push updates, fix bugs, things like that. On the Defender side, using maybe some of these monitoring systems that Brian was talking about earlier, Azure Monitor, AWS CloudWatch, etc., along with some other specialized defense tools like Splunk, the network defenders, again, using probably like a VPN connection, can monitor the system and understand what traffic is flowing through your service and how best to take action if action is needed to be taken. And finally, the most important role is the administrator, right? So the administrator is going to have the highest level of privileges on your system. They're going to be able to touch every piece of the service or every piece of the cloud-based system to administer access controls and things like that. And because this is the most important or the most elevated privilege user role in the service, we want to take a few more seconds to talk about it. So the admins typically connect to the cloud-based system via command line interface or CLI. And this typically allows them to, like I said, read and write storage data, create and destroy assets as needed, modify access control lists, etc. Because this is such a powerful role to have, all of the cloud service providers have various levels of security around those roles. So, for example, for AWS CLI, you're required to have 3 pieces of information to connect from one service to another. Say, for example, if you're a firewall trying to connect to an S3 bucket to pull some data, you're going to need an access control ID, a secret access ID, and a region at minimum to verify that you are the service you say you are or the user role that you say you are to be able to pull that data. And then here at the bottom is just the takeaway. So this CLI interface for administrative use is obviously a very useful tool for the administrators, but it can also be a very powerful weapon if an adversary were able to get their hands on some of these credentials. It could really cause a lot of harm to your system. And all of that is kind of a lead-in to the second example for Capital One that Brian alluded to earlier. So in July, I believe, of 2019, Capital One had a data breach due to a misconfiguration in one of their AWS firewalls. So what's typically supposed to happen in AWS is the user interacts with some web page that sends their traffic through an AWS firewall. The firewall requests data from the servers, and then the application servers push the data back to the user. The problem, or not the problem, but the way that the firewall is configured is it has a higher level of privilege, like I said, going back to those necessary 3 pieces of information to connect to the S3 bucket. So it's bad practice to store your credentials essentially locally on the firewall. So what Amazon is doing to get around this is using this instance metadata service. And that's essentially just a hypervisor that's storing all of these secrets for various other services in your cloud environment. And the services can reach out to that IMDS, get their credentials, and use those to authenticate to other pieces of the system. So typically what's supposed to happen, user requests information, that request goes through the firewall says, I need to talk to this S3 bucket, but before I can do that, I have to get my IMDS to give me my credentials so that I can then authenticate with the S3 bucket. After the credentials are exchanged, traffic can flow as normal. What happened with Capital One is an adversary was able to trick a misconfigured firewall using an attack called a server-side request forgery to request AWS firewall credentials from the IMDS service, the IMDS. And then because it was a normal interaction, the IMDS just gave the firewall its credentials, and then the adversary was able to capture those credentials in that exchange. And then with the firewall's elevated privileges and credentials, they were able to access the contents of various S3 buckets, those storage services on AWS. And that ultimately led to the data breach of 100 million customers' private information. So the fault ultimately fell on Capital One because this was a misconfiguration of their cloud service on their part. It was not the fault of AWS. So Capital One ended up paying about $80 million in lawsuits and then $190 million, or I'm sorry, $80 million in fines and $190 million in class action lawsuits, which is a whopping $2 a person. Yeah, so just to kind of bring it back to cyber testing, the test community really needs to understand these cloud environments because they can get so complicated so quickly, and such a small misconfiguration on the customer's part led to such a devastating loss of information. It was devastating for Capital One, but more importantly, it was devastating for all of the customers who lost a whole lot of private information. So like I said, this was not the fault of Amazon, but Amazon did step up and they made an IMDS version 2 that kind of changed, that prevents that server-side forgery request. The problem is IMDS version 1 is still enabled by default due to some third-party integrations and backwards compatibility issues. Like I said, main takeaway, testers really need to be familiar with what's in the cloud for each individual system because it can change so widely from one system to another. Really need the help of these subject matter experts when tackling cloud cyber testing. So I won't run through this list, but the main idea is it's just as important to understand how you're preparing for a test versus how you're going to execute the test. So knowing that the test team has all the resources that they need, knowing what the environment looks like, knowing what the metadata and traffic is supposed to look like for this cloud service, things like that. So this is kind of my get off the stage slide, but good cloud-based cyber testing really hinges on smart and thorough planning on not only the red team, but the stakeholders in general, right? So identifying what the government is putting in the cloud and how those services interact with one another, enumerating what those various user roles are able to do, how they're able to connect to the system, what your attack surface really looks like, and then finally making sure that the test teams know what is deployed in the cloud and how they can go about attacking it with that various levels of expertise. So I think I'll call it there, and if you have any questions, we'd be happy to answer.
We have time for one quick question. All right.
So this isn't a test question so much as is IMDS v1 still available in FedRAMP and GovCloud versions as well? Okay.
Super quick question.
Thanks for the confidence.
Well, let's thank our speakers again.